Alright, hell yeah. So we have dynamics, and I'm excited about this one. Last night I did kind of a similar problem. It's kind of in the same chapter. We're doing rotational stuff. We want to find velocity and acceleration. So on the next couple pages we'll just show the picture. But you know, I'm horrible at reading, but I just kind of read the question. It says, hey, they want to know this slider. They want to know its velocity and acceleration, like right now. You know what I mean? So we're going to take a look at that. And today's solution is going to be based on, like, 20 years from now, if I want to come back to this, where I just stopped learning anything, I could still do this problem. So, and I think that's a good skill to have, especially with dynamics. My brother was taking a look at this. Well, I don't know. My brother is an 8th grade math teacher, and it's just kind of fascinating. Like, I'm horrible with, I can't do what he does, for sure. I need a camera to hide behind, but it's just amazing. But I don't know, it's just kind of interesting when you just look at a subject that you've never, like, learned before. It's just like, dynamics, he's just like, yeah, that does not look like for me. You know what I mean? And holy hell. So yeah, we're going to do that using that strategy. Now it says this slider, and we're going to do that using we're going to try to make this problem as simple as possible. Okay, so it says that this slider moves at 120 whatevers. You know, it just moves with the velocity, millimeters per second, but it moves with this velocity around this thing. So disregard this. And then let's just make, instead of this curve shape, let's just make this a straight line. Okay, hell yeah. So now we're getting somewhere. And we have this slider P. And guess what? It's got a velocity of, no one knows what this is. Let's quickly do factor label. You know, first chapter of physics is really good. 120 millimeters per second. We can change this to whatever. You know what I mean? And so we're just going to go 1,000 millimeters in 1 meter. You know what I mean? And we could have done this. The second I said factor label, like, my brain clicked on it and be like, well, just move the decimal 3 places. So this is 0.12, and we'll just call it that, 0.12 meters per second. So 0.12 meters per second. That's the velocity. Hell yeah. And you can see, and just a lot of different ways. This is 1 divided by 1,000. You could also, and then, whoops, this is in millimeters. This is also 10 multiplying by 10 to the negative 3. And, you know, it's all the same. This could be 1.2 times 10 to the 2. You know what I mean? So now you got 1.2. You got 10 to the 2 times 10 to the negative 3. Hell yeah, let's do that. So 10 to the 2. That's going to be 10 to the 2 minus 3. We still have 10 to the negative 1. That's the same thing as 1 divided by 10. So this 1.2, you still got to divide by 10. Decimal still goes to 0.12. Alright, hell yeah, just a lot of different. I love doing that, you know what I mean? When I don't know how to do the problem, it's like, well, let's just work on the things we do know how to do. But we can do this one. Okay, so now, if this is the case, nothing rotates, and the slider just moves along a straight line with a velocity of 0.12 meters per second. What's the acceleration? Well, I can see that the problem says it moves with a constant speed. You know what I mean? So I don't know how you're going to visualize it. Just make it like this rod like a track, and then pretend like this is a remote control little vehicle that, you know, rovers along this thing. I don't know how you're going to visualize that, but I would do that. That's the first thing I was thinking, is just like, well, why is this velocity constant? How are they getting that velocity to be constant? You know what I mean? That's kind of an interesting thing. I didn't really understand that. But yeah, that's... Oh, the other thing I guess makes sense is, let's say this slider, like, dropped into this position. And, you know, so this thing, yeah, this is kind of fascinating. So this thing's rotating. Let's say it was, like, over here. And then you drop the slider drops. And by the time this thing rotates, this thing is horizontal. Well, now we know that gravity Because if this thing was over here, and then we have the slider, gravity is like dropping it down this rod. But when we're right here, gravity can't like gravity is not taking this slider and making it closer to the earth. So I get that just by geometry, heck yeah, if this is in that position, it's going to have a constant velocity. And this velocity, I don't know what it says. It says relative. See, it just says at this point. That's the other part of these problems that I don't really like, because they're just like, hey, at this one instant in time, let's find the velocity and the acceleration. But it would be cool if we could find an equation for the velocity and acceleration of this slider until it like flies off. You know what I mean? And probably we could probably do that. And even with the method that I'm going to use today. All right, hell yeah. So let's see, where are we going to go next? All right, hell yeah. So we're still going to say, hey, this thing's not rotating. We got two things going on here. This rod is not only rotating up this way at 0.8 radians per second, and we should get a visual. That's the first thing. We should kind of understand what the problem is going to look like. Because if we built this and then generated this angular speed, you would want to know if it's like hella fast, or like you could do it with your hand, or do you need a high-speed motor to get it to do its thing. But where we're going is that we're just going to neglect this, but now this slider isn't rotating in a straight line, it's going along a curve. And this is where I just don't know whether to take, a huge tangent and be like, well, if it's going along a curve, we know it's accelerating. But I can say this in very simple words. Like right now, we know that this thing has a velocity that way. Okay? We say this thing is not rotating. I'm covering that up. So if we just drop a slider and then it reaches this point with a velocity of 120 millimeters per second, and let's get a. So even this, I don't deal with metric. So anytime that we can get an idea, but I do know, like 100 millimeters, I do know this is 4 inches. It's hella close enough to 4 inches. But I think the other thing to know is, like, if I know this, what I don't really do is do, like, the two others. You can do, well, isn't 50 millimeters 2 inches? But more importantly, I think I would go right to, hey, 25 millimeters is 1 inch. Now, why don't I make this association? Well, it's just because it's an exact number. It's 25.4 millimeters. And I think that messes up the American mind converting into metric, because it's a precise number. It's kind of like asterisk, where this is. And but this rounds to 25. So at the end of the day, we should just be thinking 1 inch is 25 millimeters. And that'll just be really helpful, because then I can just totally visualize this, and I can count to 4. That's going to make up the 100. That's 4 inches plus almost an inch. You know what I mean? It would be 4/5 of an inch. You know what I mean? So it'd be 20. It'd be 20 millimeter, 20/5. Okay, hell yeah. Cool. So, yeah, and then what did I want to do? Yeah, so I wanted to figure out, how fast this thing is moving. So in real life, this is 4 inches, and we got about 5 inches. So real life, this slider is moving this fast. 0, 1, 0, 1. All right, hell yeah. And now I think what we should do with this picture is be like, okay, let's see how far it's moving on this thing. So like even just right here, we have 200 millimeters, and we're gonna go half of that in a second. So it's like, hey, this is how fast that slider is moving. So just do that a couple times, and now you can be like 0, 1, 2, 3. So this slider is moving about that fast. 0, 1, 0, 1. And I think that's pretty good. So. And since we're on this trying to get an idea of what the problem is, let's also do this, 0.8 radians. Anytime I see radians, I draw a little circle, and then I slice it up. I don't know, Trivial Pursuit style. But, you know, into 6, because there's 6 radians in a circle. There's 2 pi. It's 6.28. But basically, pretty much 6. You know what I mean? So, hell yeah. And one of these is 1 radian. But, oh, we're saying we're going only, and it's about 60 degrees. So one of these, and it's actually 57. It's good to get, like, you know what I mean? And do you want to figure out, and it's also good, like, also using factor label. What the hell is 1 radian? Well, I don't know what 1 radian is, but I do know that 1 circle, and I can just write, hey, like, what do we know? 1 circle is 2 pi radians. I know that. And I've always said in factor label, like, don't write things like this, but when you don't know anything, you probably should. You should probably write it this way, and then once you do that, then you can stack them. Or, you know, write a few more lines. I can be like, well, 1 circle is 360 degrees, is 2 pi radians. And I don't think there's anything worse to the math and physics world than symbols. Now, I guess if you see pi, you know what we're talking about, but no one knows what you're... Even with pi, no one, like... it is just involved in way too many things that I don't think people even, like, associate it with, like, the basics that it's... You know what I mean? Maybe it's just part, of, like, is pi only just a ratio of diameter to circumference? You know, is that all it is? Damn, I even forgot what pi is. You know what I mean? So we have pi d is the circumference. And the other thing I don't like is that the circumference c, that should have its own symbol. Because the letter C isn't good enough. You know, I'm going to go to the Greek alphabet and see what symbol should be for circumference, and let's inaugurate that in. Because it would help students hella. I mean, D, obviously. Any lowercase d, uppercase d, that's diameter. But, man, circumference is all on its own. I don't know what you do. Anyway. Alright, hell yeah. So 360 degrees is 2 pi radians. Again, I wouldn't write it in a line item form. I would stack them. I would say, hey, 360 degrees and then 2 pi radians. Now we have something to work with. Now we can multiply this against something else. And, you know, sometimes this is what, especially for high school, I remember high school chemistry, you would do factor label. This is like where I first got introduced to factor label, because you do moles per liter, tons of labels where you had to kind of convert units. And so one thing that I do is just, you know, totally guess. So I'm just going to throw 1 radian. Now there's 2 checks on this. Like, let's say I wrote this as 2 pi radians divided by 360, and then I just said, hey, I want to know what 1 radian is. Okay, well now, am I canceling? No, in this case I'm not canceling. So, you know, do it this way. So that's how I teach factor label, I think, is like, sure, write what write 2 things that you know are the same. 12 inches is 1 foot. But then steer clear of this and then stack them. 12 inches is 1 foot, and then do another one. 1 foot is 12 inches. And then just throw it at what you're wanting. Let's say I have a football field that's it's 100 yards, so it's 300 feet. I want to know how many inches are, you know, end zone to end zone. So let's just do it wrong, and I'm going to stack them. I'm going to go, 1 foot, 12 inches. So now I'm at least not using this, because this can get confusing, you know. But you at least know that, hey, these 2 things are equivalent. Cool, stack them, and then know that you get 2 different ones. You can stack them this way, stack them that way. Throw it at it, and then you're going to try to cancel units. Does feet cancel with inches? No, feet would multiply with feet. So this would be a ridiculous 300 feet squared divided by 12 inches, you know what I mean? And then you'd have units of feet squared per inch. Obviously not, so let's throw the other one at it. We're going to do 300 feet and then 12 inches divided by 1 foot. Hell yeah. So feet cancels, and looks like we got 300 times 12. I don't know what that is, but I do know that 3 times 12, maybe I don't even know what 3 times 12 is. Nah, I don't. Like, let's say I don't. So 6 times 6. Oh, hell yeah, that's 36. You know what I mean? So anytime that you're doing simple, and let's not mess this up, that's 36 with 2 zeros. So we got 3,600 inches. Yeah, you always want to be on top of your game to, like, hey, do the guess method first, and then make sure you're not making mistakes. So even like right here, I could say, hey, this is pretty close to 100 times 10. That's going to be 1 with 3 zeros. This could be close to 1,000. That's going to be on the lower end. I lowered this one, lowered both of them, or I could raise them both. I could say this is 1,000, and this is, well, I mean, yeah, let's not get ahead of ourselves and start just doing a guessing video. But hell yeah, so we just did factor label, and we're trying to figure out what the hell, like 1 radian. Like, you know, it's just, that boggles my mind that I don't just go right to the factor label. But even in college, I remember, you know what I mean, if something said 0.8 radians per second, and someone's like, how many degrees is that? One, I had no idea how to even guess. But now I know that 1 radian is approximately 60 degrees. That's close enough to 1. It's cool, 60 degrees. But then I know that 0.5 radians would be half of, you know, that would be 30 degrees. So 0.5 radians is about 30 degrees. Okay, so it's between 30 and 60. You know, I'm just going to guess 50. Who cares? Okay, so hell yeah. But let's do it for real. I'm going to, and then so like right here, we stacked them. This one was wrong. We didn't stack them right. We can't cancel. That's why I went through this whole thing. This one, hell yeah, we stacked them right. So now we're going to get, oh man. Now I don't think we're going to get much of anything on this. Oh yeah, we're going to get, Holy Toledo. Oh, that's so interesting. So what this is a unit conversion. So this doesn't really change anything. So what I have written here is just 1 radian. By itself, that's exactly what I want to know. It's the same thing as writing 1 foot. Cool. I know that I have 1 foot. Visually, I know that. But I know nothing about radians, let's say. And I just visually can't visualize that. Let's say I knew nothing about feet. Never heard of the concept. I'm really good with inches, though. So what would we do? We would take 1 foot down here and 12 inches up here. And the reason we can do this, 12 inches, 1 foot, and maybe I need to do this more. 12 inches is equal to 1 foot. And as a line item like this, I can see that these two are equivalent. And so when I stack them like this, it's like I'm multiplying by 1. 1 foot times 1 is still 1 foot. But what I'm not multiplying by 1, I'm multiplying by an equivalence. So I'm actually, in this case, I'm multiplying 1 by 12, but my units changed. This unit cancels it for this inches. So now I have 12 inches. And so that's what we have going on there. And this is so interesting that even, like, to this day, like, I'll pause all day and make an hour video on radians, because it's the cornerstone of people, like, for me, like, not understanding dynamics, where you're just like, nah, I just see the word radian, I'm zoned out. You know, I don't know what you're talking about. All right, so let's do it back over here. So we have 1 radian. Now we know we're going to use our unit equivalents. I know I need to cancel out a radian down here, so I can just go right to 2 pi radians. I know that 2 pi radians is a 360 degree circle. Hell yeah. And so radians cancel. And I think this also gets confusing. I remember for college, because this little degree sign doesn't look like a unit. You know what I mean? So maybe when you're just kind of practicing with this unit conversion of radians degrees, you should write maybe 360 DEG divided by 2 pi radians. Radians cancels, we have 360 degrees, but when we divide 360 by 2 pi, Booyah. And again, don't get caught up. Anytime you're reaching for your calculator, you know, make sure you got your guessing skills on. And this is going to be 360 divided by 6. Okay, and then do your picture. Hey, this is a 360-degree circle. Divvy it up 6 ways, that's about 60, right? And then this is going to be 360 divided by 6.28. So if we're going to divide by a bigger number, you know, so here we divided 360 by 6, this would be 60 degrees. But now if we're going to divide by a bigger number downstairs, that's going to make our end result a little bit smaller. So, and I think I'm pretty close for this 57.4. I don't know if it's 57.36. There's a lot of different things that come out to be 57. Like I know like tangent of 1 degree. Well, let's just do that right now. So we're going to go into degrees. I'm going to go tangent of 1 degree. No. It's tangent of 89 degrees. So tangent of 89 degrees. Now, what am I thinking? I have no idea. Inverse tangent of 1 degree. No, never mind. Okay, let's just friggin' do it. So we got 360 divided by 2 divided by pi. Oh, this is also a good skill, like especially when using your calculator. Man, you would have to do 360 divided by parentheses 2 pi and then end parentheses. Or in your calculator, you just do 360 divided by 2 divided by pi. This says that you're doing 360 divided by 2, and then you're taking 360 divided by pi. So that gets them both downstairs. And is this going to be easier than doing 360 divided by parentheses 2 pi parentheses? Yes, we saved one character swipe. And holy, I was off. It's just 57.3. So my memory on the memorization wasn't even very good. So 1 radian is 57.3 degrees, and that does that. But yeah, that's also the bummer when about these problems where you can just get so focused. You can just get so focused into the details, and then you get numbers that, you know, you gotta, you know, like keep them stored and all that jazz. All right, so let's get back to figuring out what 0.8 radians per second is. Let's use factor labels. So we got 0.8 radians. We're going to do 2 pi radians, and then we're going to do 360. And I'm still a little bit new to this, so we got degrees. So we're going to go 0.8 times 360 divided by 2 divided by pi. Booyah. And this is going to be 45.83 degrees. Did not see that coming. You know, honestly, now I know if I ever see 0.8 radians again, that's 45 degrees. Call it almost exact. So now, this thing is going to be rotating. So, what do we say? Well, let's neglect this slider, and it's sliding around now we're just focused on the rod. So any point on this rod, well, I guess so it's going to rotate 45 degrees. And I was going to confuse it with 90, so let's take our time. So here's going to be 45. Here's our radius, and oh, booyah! And this is kind of cool. This point will travel, you know, hell yeah. This point's gonna travel along this circle. And hell yeah. And I just want to draw this in because this circle is bigger than this circle. This circle just has a diameter of 200. This circle has a diameter of 400 millimeters. Okay, hell yeah. So in 1 second, this rod is going to be there because it traveled 0.8 radians. You know what I mean? Could we have done that in our head? We knew that 1 radian was 60 degrees. You know what I mean? So 30 is half. And we're going to go, you know, and you could have just done this too. If this is half and this is 1, we can go 0.6, 0.7, 0.8, 0.9. You know what I mean? So there you go. It's just, it looks like it's a little bit more than 45 degrees. And it's pretty much right on 45. So hell yeah. So this point's going to go 0, 1. It's going to get up to about 45. In 2 seconds, it's going to go 0, 1, 2. And then, so let's do a full revolution. That's important to do these problems just to get a feel for this. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So one revolution is about 8 seconds. Hell yeah. Now, how do we use factor label? I swear I'm totally horrible with radians. How do we use factor label method to actually figure out what one revolution is? Because we're given this angular speed. Let's just write it. So we got 0.8 radians per second. And now I need to cancel radians because we want to know... because even right now, my muscle memory is popping in place. I want to know revolutions per second. You know what I mean? There you go. I want to know 360 degrees per second. So those are equivalent. But this is the thing where there's some things about polar coordinates. I don't even know if you call these polar coordinates. That's how bad I am at rotational dynamics. But I love it because it's so intriguing. It feels like... you know, to have a pretty decent understanding. And yeah, when we're just once we get to this problem, we're just going to solve it using like the stupidest method, I think. Anyway, cool. So yeah, but I remember just being in college and I couldn't even get a handle of that, you know, like angular speed, like if someone says, "Hey, I'm gonna do a hey, I'm gonna like I was thinking about a skier doing a 360. Let's say I'm gonna do a really slow 360. So like I'm gonna go off a jump, and I'm gonna get 3 seconds of air time. I don't even know if that's humanly possible. But hell yeah. And let's say 2 seconds of air time, and I'm gonna spin a 360. So looks like I'm going about 90, and even right now I can do this. I'm going to go 1.6 radians per second. This is really good for me to do. Because if 0.8 radians is 45 degrees per second, and that's all I was getting at. Like when you see this as an angular speed of 0.8 radians per second, no one's light bulb goes on and be like, oh, aha, like I now have some understanding of this. Hell no. But if I said, hey, this thing is spinning at 45 degrees per second, all right, it kind of sounds odd, but I get it. Like, so now I'm going to do this slow 360, and I'm gonna go 90 degrees per second. I have to go 180 degrees per second. Sorry about that. If I go 180 degrees per second, I'm going to do a 360 in 2 seconds. So we're going to go off a jump. We're going to go 0 and then 1. You know what I mean? 0, 1, 2. And then I did a 360. So 0, 1, 2. So that's the 360. 0, 1, 2. I don't know. But yeah, it'd be kind of fascinating to actually look up a video to be like, hey, what's a slow 360? Alright, hell yeah. So we're back, and what I did is I looked up, I'll link it in the description, there's a skier that does a big 360, and it takes 2 seconds. I kind of did a stopwatch. So that's going to be 2 seconds for 360, and you know, let's write an equivalent. That's going to be 2 seconds is going to be equal to, like, basically 6 radians. Okay, so if I say 2 seconds is 6 radians, well, cool. What's 1 second? That's going to be 3 radians. So that's going to be the angular speed is 3 radians per second. Where we said this was going to go at a speed of 45 degrees per second. So that's going to be, you know what I mean, 1, 2, 3, 4, 5, 6, 7, 8. It's going to be 8 seconds to get around. And then, you know, just compare it to something else that we know. And I guess I just got hooked into watching a couple videos, so I don't even know where the hell we are. Alright, hell yeah. But I thought about where I want to go next. You know what I mean? So now we kind of know what 0.8 radians per second is. Oh yeah, we were trying to do this factor label. So hell yeah. So I can just instantly see. What I'm trying to get is radians per second to degrees per second. Or maybe just revolutions per second. I forget what kind of tangent we were going on. But I can definitely change this to, well, let's do revolutions. I just want to know how many revolutions. Is that what we wanted? I have no idea. Well, no, we were thinking degrees. But let's do degrees first and then revolutions second. So I'm just going to do 2 pi radians is 360 degrees. I think I'm okay with canceling radians and having degrees per second. And I guess that'll just have a unit like this. I wouldn't write it like that. I would probably write it degrees per second. But alright, so now we can put this in our calculator. 0.8 times 360 divided by 2 divided by pi. And yeah, this is going to give us that 45 degrees. 45 degrees per second. If we want to do revolutions, we're going to do 0.8 radians per second. And then we're going to say there's 2 pi radians in 1 revolution. So radians cancels. Now we're just going to have 0.8 divided by 2 divided by pi. Alright, sweet. And yeah, this gives us about 1/10 of a radian per second. You know what I mean? So it's going to take about 10 seconds to go around. And what's 1 divided by 8? Yeah, so it's closer to 1/8. You know what I mean? It's also good to kind of know your fractions. So yeah, you can see this 1.27. Hey, close to 0.125. And I even think 1/8 that's always a tricky one. You know what I mean? And, I mean, you should always work backwards. 1/4 is 0.25. And then what's this divided by 2? That's going to be 1. You know, like, and this will help with other fractions. You know, I obviously know what 2 divided by 2 is. That's going to be 0.1. But what's 5 divided by 2? That's 2.5. So 0.125. Alright, hell yeah. So let's grab a new sheet of paper and start solving this. Alright, so, but I'm going to assume, like, hey, if this slider is at point B, and this is our angular speed, I do know what the velocity of this point is, like, even just right now. Like, right now, I know the velocity of this point. And maybe this is kind of hacky or trivial, that I just kind of know that the velocity of like, this point is going to be a tangential velocity. If this thing's spinning, you know what I mean, I'm going to have a tangential velocity. Like, if I have a disk that is pivoted in the middle, and then I have some sort of radius, and this thing is spinning with in units of radians per second, or just whatever. If it's spinning with an angular speed, I do know that the velocity right here is a tangential velocity. And so I'm just going to say this velocity is going to be, but yeah, this is kind of where I get hacky, because I also say, like, hey, no one knows what radians is, so how do we get you know, something that we don't know into something we do know? I always say, like, hey, radians times radius is something normal. And there's 3 ways to do this. It's radians per second times radius. I think you get the picture. And then radians per second squared times radius is the something normal. So the middle case is probably the easiest. Radians per second times radius is going to give you tangential velocity. But, you know, I always do this, is like, you know what I mean, like, what is 1 radian? It's about 60 degrees. And why is that? You know, it's 57.3 degrees. We figured that out. Because this is the radius right here. And if we measure this radius of this circle with a string, cut a string to that length and then drape it around the circumference, we'll only get to there. And you would do that 6 times. And not only 6, but 6.28. 6.28 times. That's how many radiuses are around a circle. That's the definition of a radian. So if we say, and if we know that, hey, we're going to do this 57.3 degrees, this 1 radian, if we do have 1 radian, and that's an angle, so you can still say an angle. That's the other thing that's kind of confusing. It's just like, what are well, like what is a radian? Well, we do know that 445 degrees, hell yeah, that's going to be that angle theta. Same thing, you know, we're saying 0.8 radians. You know, I mean, we already figured now. So we learned one thing from this video, is that 0.8 radians. If I ever see that again, I'm going to be like, oh, hell yeah, that's 45 degrees. It's a little bit more. I can deal with that. But that's the same symbol. You know what I mean? It's an angle. So we have an angle in radians. So, hell yeah. You know what I mean? You could say this angle A. I don't know. Do whatever, but just theta. That angle is just an angle. Alright, so if we take that angle of 0.8 radians, which we know to be, I guess, what are we going to do first? I guess we're going to go back to this one. If we take 1 radian, and then let's say this is, well, yeah, let's do it for our problem. So we're going to take, oh, there is no angle here, though. That's a bummer. I guess, yeah, we'll just do this. We'll just make up something. You know, that's where you just do like 1 meter. Be like, well, okay. So 1 radian is our angle times the radius of 1 meter. What does that give us? This gives us arc length, and that's going to be our, you know, as an S. That's probably also, when we're talking about polar coordinates, is like the most, like, you know, it's a good letter for it. Maybe not. I don't know. S, arc length. Like, does the word arc length? Holy hell! Look at this. The word arc length doesn't even have an S in it. So why would you use this symbol for arc length? Again, pretty horrendous, and they're just not making it any easier to learn polar coordinates. Alright, hell yeah. But so that's going to be this. Radians times radius is arc length. Radians per second times radius is tangential velocity. Radians per second squared times radius is acceleration. And it's tangential acceleration. So, and, you know, this, I guess I should do it over here. So this is in radians. That's just going to be this theta. That's typically how they're going to do that. And then radius. So sweet. And then this one's going to be omega times radius. And this one's going to be angular acceleration times radius. So this is angular speed. This is just the angle. So we have angle, angular speed, angular acceleration. But I swear it's really good to say these things because they're a mouthful. Even saying angular speed. Every time I see this omega, that's why professors just call it omega. Because even them, they'll just be like, what is it? Angular speed? Yeah. And anyway, hell yeah. So we're just going to take bite-sized chunks out of this problem. We'll get there. But yeah, it's just important. Like any of these problems, it's good to just make your foundation. Because even this is still a little bit hackish for me, because it feels like, even for me, this isn't a fundamental. This seems like a trick where I'm just kind of like, it's just a trick for me not to mess up and get a free equation out of the deal. I'm definitely not proving anything here. But I guess I did. I proved that if I at least start with radians. And now let's take this one step further. So we drew a circle, we did what 1 radian is, and we kind of figured that out. We cut a string and drape it. Okay, so let's say we do have an angular speed of 1 radian per second. Again, we're going to go around this circle in about 6 seconds. 0, 1, 2, 3, you get the idea. And so now what does this mean? This means that, hey, something is moving along this circle, or this circle is, if this circle is rotating with an omega of 1 radian per second, and this is point A, in 1 second, this point A is going to be right there. So, hell yeah, we have A0, and this is A1. In 2 seconds, this point is going to be right there, A2, A3, and it's going to take A6.28 to go all the way around. You know, it's going to take. Anyway, sweet. So that was kind of proofish. Not really. Alright, so now let's take it back to our rigid bar, because this is kind of interesting. Because even if we have a circle that has a radius out here, and then we're spinning it at 1 radian per second, and this is point A. Well, let's say a point halfway is point B. Now, and now I want to know what's happening at this point. Well, in 1 second, point A is going to be right there. This is A naught, this is B naught. Well, guess what? B is going to be right there, B naught. And the same angle got played out. So if I say, hey, this is my original angle, angle initial is 0 degrees or 0 radians, and then but angle at time, in 1 second, my angle is going to be 1 radian, or it's going to be 57.3 degrees. And so the angle, and if I say angle of A at 1 second, well, that's going to be 1 radian and 57.3 degrees. And that's going to be the same thing as angle B at 1 second. These are going to be equivalent. So hell yeah. So even like right here, if I go to point P, and then I run this thing for like a second, the angle is going to and I say that this is just going to be whatever. Let's do an angle. So we're going to say angle P naught, the initial angle, and then in so yeah, if that's the angle right there, and let's then cool. In 1 second, we're going to go about 45 degrees. So in 1 second, this slider is going to be right there. This point B also is going to be up here in 1 second at 45. Hell yeah. So that's kind of interesting that as long as this is a rigid body, that every location on here, if it's going with an angular speed of 0.8 radians per second, is going to move that angle. And I think that's one of the most overlooked things when we're talking about angular speed, is like omega is units of radians per second. So this is like it's the change in the angle. The change in the angle in radians per, kind of change in seconds. But because we have a unit second, it's literally the change in radians per 1 second. That's the units on this. Alright, hell yeah. So take a little break, but we're back. And it was just kind of interesting where, if we have something falling, it's just, it's super easy. Because, I don't know, you drop a rock off a cliff, you have this acceleration, it's 9.8 meters per second squared. I definitely use integration because, and I don't know, it's just getting used to this. The equation for acceleration is change in velocity, change in time, and then I go dv dt. So hell yeah, this is the equation for acceleration. It is dv dt. And then so that is, I can substitute that in. So I have 9.8 is dv dt, separate variables, and we got 9.8 dt is equal to dv. Typically I write it the other way around, but we have dv is 9.8 dt. I'm going to integrate, and then I'm going to have velocity. An equation for velocity as a function of time is just going to be the integration of a constant. And so you could say this is 9.8 t to the 0. T to the 0 is 1. And then so when we integrate t to the 0, so if we do integrate like 9.8 t to the 0 dt, this becomes 9.8 t to the 0 plus 1 divided by 0 plus 1. So we get t to the 1, 9.8. So, I mean, just really simply, it's just 9.8 t plus a constant. And for problems like this, where you set your velocity is equal to 0, at time is equal to 0, so we just say, hey, our velocity is going to be 0 when this time is 0. So 9.8 times 0 plus c. This is 0. 0 equals 0 plus c's got to be 0. All right. But, and it's just so fascinating. But if we throw the ball down with an initial velocity of like 10 meters per second, well, that's what it's going to be. So our velocity at time 0 is going to be 10 meters per second. Now we're going to have 9.8. Time is 0, so this is still 0, plus c. And our constant has to be 10, because we have 10 is equal to 0 plus c. And then it just has to be 10 meters per, for the equation to work out, Hell yeah. So we're going to have a velocity equation as a function of t is 9.8 t plus 10. And it's just so fascinating that we can do the same thing. I didn't want to do that, but I might as well, because like even I'm kind of learning on the fly. So this is king right here. And if the problem says, you know, our angular acceleration, but it really only says the angular acceleration at this point. Like for this problem, it says the only thing that's constant is this velocity, but it might just be constant at this point. You know, that's the only thing about these problems where, yeah, let's read it, I guess. So the collar piece slides from, oh, so I didn't even read this. So it does. The collar piece slides from A towards B along this. So it does. It starts right there. And cool. The rod rotates about the pin A, but the only way it would do that, I think, because if we, is if something is inducing that rotation. You know, if we just drop the system, it would just drop this way. Okay, hell yeah. So something's inducing this rotation of this rod. Cool. And it rotates about that point. The speed of P, yeah, again, relative to the rod is just a constant. But yeah, that's the only thing. It's probably just constant at this point. We talked about that. It's not accelerating, like, you know, along the path because of gravity, let's say. When the system is in the position shown, yeah, that's why all these problems are just like, hey, just in this little snapshot in time, the angular velocity is this, and the angular acceleration is that. And then for this position, determine the velocity and acceleration of vectors p. Yeah, and so that's all we can do, but we could just assume, hey, let's just assume that this acceleration is constant, and it's going in the opposite. It's kind of slowing this down. So in 1 second, we're going to be going 45 degrees. But in that same second, our angular speed is going to be reduced by 0.5. So it's going to go from 0.8 minus 0.5. That's going to be 0.3. And it's going to be continuous, but you could just say, hey, let's just say for the first second it is going to go 45 degrees. So this point B is going to go 45. And then in the next second, it's only going to go 0.3 radians. That's about half, so let's say it goes about, 20 degrees, or about, yeah, about that. So the first second, this thing goes 45. In the yeah, I guess we'll just, man, I wish I lowered this thing because it's kind of out of view. But yeah, in the first second, it goes 45. In the second second, well, it's going to go slower. It's only going to go 20. And then in the third second, we're going to have 0.3 minus 0.5, and that's going to be negative point. So you can see that it's going this direction, but then it slows down. It'll hit a stopping point, but if this acceleration is constant, it's going to rotate back the other way. And if that's the case, it'll just keep rotating the other way and then actually speed up the other way. You know what I mean? So a lot of these problems are just useful for like a very short snippet of time. Like, and then you should have that. That's like the first thing, I probably should do is set some limits on this problem. Let's do that right now. Okay, so one of the limits that I see on this problem is it says this slider is traveling at a constant speed of 120 millimeters per second. But yeah, that's so interesting because these problems aren't involving any mass. It wouldn't matter anyway because they're instantaneous. Like you're saying, hey, yeah, this does have mass and this does have mass, but all they want to know is the instantaneous velocity and instantaneous acceleration. So it really actually makes it difficult to bring this slider all the way up here. But let's just, for whatever reason, pretend like this thing is on a motorized track. Like literally there's grooves in here, there's wheels, and this thing is literally moving itself along from this point, which we're calling P to B. And it's doing so at 120 millimeters per second. So again, we said just visually, this is 200 millimeters. So this thing, in 1 second, it's going to go about that far. So, okay, let's do it. So 0, 1. So how many seconds is it going to take to get over there? Let's just do it. Let's just go, so 0, 1, 2, 3, maybe about 3 seconds. And did that make sense? Because if, like, what is this distance? If this, and that's tough. Like, if I say, hey, this is the radius, what's the distance of a quarter circle? It's like, well, I don't know. But if I know this is the radius, I would go all the way to diameter, even though radius, because it's really hard. I mean, you can go back to that times 6, or times 6.28, or that times 2 pi. You know what I mean? So if I do have a radius, and then I have an angle of 2 pi radians in one circle, then what's the circumference? Well, and we should be getting used to that. You know what I mean? It's kind of 8th grade to be like, always use the diameter. The only way I know circumference is pi d. You know what I mean? Well, get over it. And maybe I'm just losing my mind. Where I typically don't do 2 pi r. You know what I mean? But yeah. But this doesn't follow that same, like, circumference. Like, let's do this axiom. Radians times radius is arc length. Okay, so the radians is going to be 2 pi, and then the radius is going to be... Yeah, I had no idea that this even follows. I figured it was going to be in reverse. You know what I mean? Sometimes that happens where, you know, you take an equation like this, where maybe it's just more natural to be like radius times radians, but not in this case. And then, you know, for whatever reason, people just, you know, bring the numbers and the constants to one side. And then, especially with equations involving a lot of different things, like the one that I can think of is mass moment of inertia, the second moment of mass. I mean, just by definition, oh yeah, I kind of even forget what that equation is. Oh, hell yeah. No, let's do this. If I can't, I love this mass moment of inertia, or moment of inertia, you know what I mean? Unless you're talking about an I-beam, and then you're talking about area moment of inertia, which would be just called second moment of area. And I love this because we know what a moment is. If you have a door and you're applying a force, and then here's your distance, you know what I mean? Hey, the moment is force times distance. FD, or moment, is force times R, FR. And this is the first moment of force. You know, so it's just kind of cool that this is the second moment of mass. So it's just like, what the hell does that mean? Well, it says that, hey, we have some sort of mass, and the distance, and what makes this first moment is the distance. You know, we're having leverage. We're identifying this force, but it's a distance away from the hinge. And that's what's giving the moment, you know what I mean? That's what's giving the leverage. So, yeah, anytime that you hear the word moment or second moment, you know, it is a leverage game, you know what I mean? So if you have an I-beam and you have the second moment of area, the area is out here, it's leveraged, you know, it's where it needs to be to provide that, you know what I mean? So for this second moment of mass, I know we're on a tangent, second moment of mass would be mass times the radius squared, mr squared. Oh yeah, and I have no idea, because there is something called like I omega. Is that right? Man, I'm just mincing videos now. This is awful. Alright, hell yeah. No, this is sweet. This is going to be such a good side. And this is kind of my day off. Like, I just really don't care. So we're just going to be, you know, kind of doing this type of stuff. It's just like, hey, like because I think I omega is angular momentum. So that's where I'm at right now. You know, I've done angular momentum problems, but it's just like if I see I omega, I have no idea. So this will really solidify it, because I just started with what mr square is, and I know where I'm going with this. So this L is going to be angular momentum. And we made a video on that. And what is angular momentum? And we can just say it. It's the first moment of momentum. So cool. And I love this analogy that what is a moment? You know what I mean? Because if you're saying first moment of momentum, holy hell. That is confusing because you have two different things with that, like moment and then momentum. Those seem similar. Yeah, so my bad on that. But what is a moment? Hey, you're identifying something that's driving the force, and then you're, it's this leveraged force. And as a vector, these hinges are going to rotate like this, or opposite, basically. They're going to rotate like that. And anytime, and this also applies to our problem. Because I was just thinking about this. It's just like, because this textbook kind of sucks because they don't really explain too much. They give you sample problems, which are cool, but it's just like, I don't know. You know what I mean? Like I said, we're doing this one because in 20 years from now, I'm going to come back and do it the same way. I'm just going to kind of roll through these basics. The basics, I probably will, but we'll get to the problem in a second. But yeah, what I'm saying here is like, hey, you use right-hand rule, so this is having an angular speed. That's why you call it omega, because like I just kind of paused it. It's like, what the hell is this called? It's an omega, but it's angular speed. It's radians per second. It's a change in angle of 0.8 radians per second. So I love doing that, where you're just saying, you know what I mean? Hey, it's omega. What the hell is omega? It's angular speed. Cool. So we could write that, angular speed. It's also a change in angle. So we're changing the angle with a change in time. You know what I mean? Sweet. And that's also theta dot. You know what I mean? It's the derivative. So it's d theta dt. This is, you know what I mean? So these all are omega. And it's just kind of fascinating. It's radiant, yeah. Cool. All right, hell yeah. So, yeah, back to angular momentum. Angular momentum is the first moment of momentum. So we're going to have, and I don't know how you're going to write this. Like, I think it typically gets written like this, R cross MV. You know what I mean? And then R is these are all vectors. And that's the reason I brought this up, because hell yeah, if this is a right-hand rule vector, it's coming out of the page. And I would do a double arrow on it. I still haven't found out anywhere where they do double arrows, but it indicates that, like, hey, it's like a... And my brother probably, he cringed at this, I think. It's just like, nah, just because especially in these problems, well, everything's just a vector, get over it. You know what I mean? You could have a position vector. I think that's the confusing part, is if, like one of the problems, it had, it would be like, hey, this is a bar, and then this is another bar to a slider, and this is point B. So... like what? And look at this. Like this is your position vector, and they would do an R with an arrow. You know, maybe position vector OB. And worse, like I don't know, they will do OB like this with a slash. And no, that's a relative term. So maybe I don't know. I don't know what the slash is. You know what I mean? Like who the hell cares? But this is a position vector. Where now, like, check this out. This B could have a position vector. All that is just this distance. You know what I mean? BX, and then BY. Got it. And then, hey, this thing is rotating with an omega. And this is a vector. And obviously, you know what I mean? It's going to be into the page. Maybe do a double arrow. But that's where my brother's like, maybe don't do that because it's just a vector. You know what I mean? And then, so this is going to have a tangential velocity. So we're going to have a velocity of B like that. Well, what's the equation for this velocity? And it's just kind of fascinating that the equation for velocity, this is the something normal, so just back to the hackish way of going about this, that's going to be my omega times radius. It's going to be radians times radius is something normal. And again, this is angular speed, so it's radians per second. But just the word, radians per second times radius is something normal. That's tangential velocity. So if I was trying to find the tangential velocity, that's going to be omega times radius. But hey, guess what? This is kind of the scalar way to write it. And we know, all this crap is in plane. And that was kind of interesting. They say, like, hey, this is planar motion. So let's take this and, it just, by the picture, it looks like everything is in a plane. But hey, let's take this point and move it out to here. And then this arm is going to be kind of at an angle. So we kind of have an angle kind of in here with the horizontal, and it's still moving. You can imagine you can imagine like this. If this is an aperture that's moving like this, and and here's point B, well, I'm going to just kind of lengthen this aperture out to here, and I'm still going to have the same angular speed this way. So if I look with a view like this, it's going to look identical. But what happens is this radius vector from this point, if this is the origin, and we're going, into we have our x, y, and then, here's our z-axis. And so now this position is going this way. But if we're still rotating, if our omega vector is still just right here, this omega, so omega is going to be, for this, it's going to be 0.8, and it's going to be in the z. So this is the k hat direction, this is the I hat, and this is the j hat. So we have 0.8 k hat radians per second. Okay, so now, what do we multiply? So we just kind of stretched out the problem, did a horrible job of drawing it, but I think you get it. But we're not going to take this new distance. We're only going to take, and for the problem, this was just 5 inches. This original length. And now let's say we bring this all the way out here to 10 inches. Well, we're not going to use this 10 inches at all. We're just going to use this 5 inches. And how would you do that as a vector is, for this original problem, this 5 inches, and let's say we just have 45 degrees, keep it simple. Oh man, I don't even know if this is keeping it simple at all. And what we would do is we would just, just by observation, if this is 45, we'd be like, okay, well, this is going to be 45, this is going to be 45, this is going to be 45. So by observation, this tangential velocity, and we're going to do omega of just 1 radian per second, just for our example problem. All right, hell yeah. Yeah, so we would just do 5 inches times 1 radian per second. Isn't that the definition of tangential velocity? Didn't we say radians times radius is tangential velocity? So we want to know this tangential velocity of B. That's going to be that 1 radian per second times the radius of 5 inches. Units mesh up. We have 5 inches per second. That's going to be our tangential velocity, 5 inches per second. Sweet. But this tangential velocity is tangential, so it's going to be in this direction. So it's going to have 2 components. And we can see that we're going to have, so this is the magnitude of our tangential velocity, but you can see it's going to have a component in the I hat direction, and it's going to have a component in the negative j hat. And it's going to be a 45, so like they're going to be the same. So what are these 2 components? Well, it's going to be, and that's where it is kind of fascinating. We can draw a little triangle, and they do this all the time. It's like, well, this is your tangential velocity, and it is this side of this triangle is 5 inches per second. and these are 45-degree angles. So what is this dimension? You know, you can just look at it, and I didn't really draw a 45 very well. But if this dimension is 5, what is this? Well, it looks about like 4, 4.3. Same thing here. It looks about 4, you know, 4 point, you know. So anyway, and let's see if I guessed right. I'm just trying to get more in tune. And that's probably actually not quite right. Because I do know if, like, oh, damn it, what do I know? I'm just going to guess 4. 4 and 4? Is that, because 4 squared is 16, 16. Yeah, no, it's going to be less. It's that these are actually like 3.8. Yeah, holy Toledo. Because, yeah, what's 5 divided by 1.5? That's 3.3. So, yeah, because here's the trick that I do with 45. Like, let's say I didn't know what this hypotenuse was, and I had a component that was, we'll just say 3.3 and 3.3. These are 45-degree angles. What I do know is at most, like just a really quick guess, and it's an overestimate, is just take one of these numbers and multiply by 1.5. So we got 3.3 times 1.5. Hell yeah, that's about 5. And so why did that work? Is because 1.5, what we're trying to equivocate is 1.5 is very close to 1.4142 or whatever. You know, square root of 2. Hell yeah, 1.4142. You know, close enough to 1.5, and it really gives you a guessing thing. So we can even take 5 and divide it by 1.5. And we can say, hey, this is pretty close to 3.3. So that's kind of a really cool way to get the components. And as long as you have a triangle that's not super messed up, like let's say we have a 3, 4, 5. So we have 3, 4, and 5. Can't we do the same thing? What I would do is say, hey, just take well, I don't know. Would I do 4 times 1.5? Like 6. It's the biggest it could be, but 3 times 1.5. Yeah. So, yeah, that's kind of an interesting tool. Is just, hey, take the biggest number here, which is 4, times 1.5. That's going to give me 5.5, right? I don't even know. No, it's going to give me 6. Yeah, that's going to give me 6. So, and if these were both 4, if you had a triangle that was 4 and 4, well, hell yeah, that kind of works. 4 times 1.5, obviously 6. And it's going to be a little bit less. It's actually going to be 4 times 1.4142. You know, this is actually going to be 5.65. So how do we do that? You know, it's Pythagorean's theorem. And I'm just kind of going over how you can kind of guesstimate that. And so, yeah, so let's do this one. How do you actually find the hypotenuse? Well, you're going to do a squared plus b squared is this side squared. So if you just want that side, take the square root, and then you actually get this. So we're going to have 4 squared plus 4 squared, square root of that. Well, 4 squared is 16. So we're going to have 16 plus 16, square root of it. We're going to have the square root of 32. Now, let's try to do some guessing, because we got the square root of 25. Hell yeah, and the square root of 36. These are the ones that actually jive, you know, 5 and 6. 32 is pretty close to 36. So now we can kind of see that, hey, we're about maybe 5.8. I don't know. That was a pretty good guess. But it's a little bit less, and we just actually do it. Square root of 32. Hell yes, 5.65. There you go. And 4 times 1.5, it was an overestimate, that's for sure. But it gets us in the ballpark. You know what I mean? We were saying square root of 32 is pretty close to square root of 36. Alright, so holy hell. So why did we even do that? Is because we were trying to find the components. So just right off the bat, if I say, hey, this has a tangential velocity of 5 inches per second, what's the component in the x? What's the component in the y? 5 divided by 1.5, close enough, 3.3. How do we do this for real? we see that these components, a and b, are the same. C is 5, so we're going to go a squared plus b squared is equal to c squared. We know that a is equal to b because it's 45, so we can say, like, hey, that's a squared plus a squared is equal to c squared. That's going to be 2a squared is equal to c squared, and it's going to be the square root of 2a squared. No, we want to solve for a, so sorry about that. So we have 2a squared is equal to c squared, so we actually need to bring the 2 downstairs over here, and then take the square root of it. So a is going to be the square root of 0.5 times 5 squared. And I definitely don't know that one by heart, but that's going to be 3.5. But see how the actual equation to get these sides, you could mess that up. That's all I'm saying. But it's just kind of easy to go 5 divided by 5 divided by 1.5. That gets you pretty close. You know what I mean? So 3.5 is pretty close to 3.3. You could do 5 divided by 1.4. That gets you even better. 5 divided by 1.412. Obvious. 4.4142. That obviously gets you right in there. You know what I mean? It is essentially it. And you could just know that it's the square root of 2. So you could just get fancy and be like, hey, 5 divided by the square root of 2. And that's pretty wild. Is that all we did here? This was just, because yeah, let's do this one. Because if we have this side is the square root of 1/2 c squared, and this is such a good trick, is you can just, we have, anytime that you have a product or even a quotient of things, you know what I mean, it doesn't really matter, you can just, you could do this. So, oh man, let's grab a new sheet of paper. Hell yeah. So we're going to have a is the square root of 1/2 c squared. And then we're definitely going to get back to this angular momentum. Alright, sweet. So what you would do is you could just do this. The square root of 1, square root of 2, square root of c squared. I mean, hell yeah. So, I mean, obviously this is just 1 divided by the square root of 2, and this c squared is just c. So we have c divided by the square root of 2. And then the square root of 2 is just that c divided by 1.4142. And isn't that what we just did? Our c was 5. 5 divided by the square root of 2. That is exactly what we did. You know what I mean? So, but that might be difficult to memorize. 5, the hypotenuse divided by the square root of 2. You know what I mean? I think that's too complex, where you can just think, hey, 5 divided by 1.5, and it's just mentally you can. I don't know if I could do that in my head, but you could obviously do it in reverse. You can always take these numbers, multiply by 1.5. Even if you have a triangle like this, it just gets you in the ballpark. You know what I mean? Where you're yeah. Anyway, all right, hell yeah. So what did we just do? We saw what vectors are. We talked about how this angular speed is a vector. It's in the k-hat direction. And so why that was useful is because in this problem we had angular speed of 1 radian per second, and we had an arm out to 5, and it was just really simple to say, hey, 1 times 5 is 5 inches per second. But how would you do that with vectors? So this problem, I guess we have to kind of redraw. So here's our 5 inches. Here's our 10 inches out to this point B. Sorry I didn't draw it any better, but obviously, yeah, cool. So this is going to be your k-hat, your j-hat, and your i-hat and j-hat. Basically your x direction, your y direction, and always do the right-hand rule, and hell yeah, that's going to be your z direction, your k direction. Whoop, whoop, whoop. Alright, hell yeah, getting a little sloppy. But anyway, yeah, this is fascinating because even in the books they do this, and I don't know, I don't get used to it. Because it's kind of like a statics. It'd be something you would do in statics, hell yeah. But it's just like dynamics, there's so much going on, it's just like, well, I don't want to do everything or something. Kind of get lazy. But we can take this position vector, we're going to have, maybe I shouldn't have called this 10. Let's just say this is 5. So this position vector, well, what is it? It's going to be 5 times the square root of 2. That's 5 times 1.5. So this is about 7.5. So we're going to have 5 times the square root of 2. So now this distance is actually going to be 7.07. And you can call, divide by 10, that's 0.707. And that's like sine of 45, cosine 45. You know what I mean? So, hell yeah. And sorry I didn't draw it right, but we have 5 inches in the z hat, in the k hat direction, the z direction. We have 5 inches up to here to this b. So to get from point O to B, we would have to go in the x direction 5 inches, in the y direction 5 inches, and then in the z direction a negative 5 inches. All right, so let's do that. So that is literally the definition of our position vector from the origin to B is, let's say that again. It's 5 in the I, so we have 5 inches in the I hat plus 5 inches in the j hat plus negative 5 minus 5 in the k hat. Okay, hell yeah. And then what's our omega? Our omega is 1 radian per second k hat. So when we multiply these, we multiply them with the cross product. And I think, hell yeah, just get a little situated. And I think this can be now, so let's get everything, So now when we do this omega as our, k hat, and then even right here, we have this bar up to, no, we're having this new bar to here, but it is rotating, I guess it's rotating this way. Oh no, like which way are we having this one rotate? Oh, I guess we are having this one rotate in the negative k hat. So this one's negative 1 radian per second. So there you go, because it's rotating this way. Hell yeah. So if this is our angle, initial angle on this thing at a 45-degree angle, it's rotating at 1 radian per second. Cool. Alright, we got it. And we want to know the tangential velocity. But you can see here that this tangential velocity is a product. Like this was the something normal, so it was radians per second times radius, and this is good because, okay, so here was our omega, and we do this vector in a curl, and that's probably hella confusing, because why don't you, like in this case, why don't you just do the right hand rule and call this omega AB? You know what I mean? Hell yeah. And then you're gonna use the right hand rule, and then this is the angular acceleration AB. Cool, they're vectors. And then, because then you can see that, radians per second times radius, we were just multiplying omega, the angular speed times the radius, that is the tangential velocity. But how do we do that with vectors? You know what I mean? Because if we have vectors, and this is maybe a cool thing for me, I guess. Oh, this is blowing my mind. If I have a vector, I can't just do this to vectors, I guess. Man, this is fascinating to me. I never really thought about this. This is esoteric. You can't just multiply vectors together like this. Is that true? Like you can't multiply 2 vectors. The only way, because there's 2 different things going on. If you are going to multiply vectors, this is so fascinating. I mean, you either take the dot product, you know what I mean? And this is the incorrect, this would give you something nonsensical probably. Or you take the cross product, which would be omega cross r. And I even think I have this written wrong, where you have to do r cross omega. You have to, and that's fascinating to me, of like, because r cross omega, this will get you the right answer. This will give you negative. It'll give you the inverse. It'll give you a vector, but then you have to like product through a -1 if you do omega cross r. So yeah, so when we do cross products, oh, that's fascinating. And I guess this also, like going back to what I said about a moment being the first moment of force, I guess moment, you would still do it R cross F. Holy hell. You know what I mean? So you would actually do it in this order. You wouldn't do the force times, you would do the distance first times the force. And that's fascinating. That's why when I was starting to write angular what is this called? Angular momentum. You do the distance vector first, crossed with the momentum vector. So this is r crossed with momentum. Momentum is a product between mass and velocity. Mass typically doesn't change, unless you have like a rocket ship where you're losing fuel and mass. All right, hell yeah. But even in the case, I don't even think it's a vector. You know what I mean? Yeah. Even if you're losing or gaining fuel, like putting a vector on mass means that it actually has scratch that actually. I don't know. But, if you have a chunk of mass, it's not changing, so it's going to be kind of the same. That was an awful definition. But that's why it doesn't carry a vector. All right, holy hell. All right, I'm still enjoying myself on this one. We haven't gotten very far. But I guess I do know now that r cross omega is going to be my velocity, tangential velocity, and it's a vector. So let's do that one. So we're going to have this r and this omega cross. So we're going to have 5i plus 5j minus 5k crossed with negative 1 k hat. Okay, hell yeah. So to do the cross product, you need, I would do this. This is the most sane way to do the cross product. You already know that this is the x, this is the y, and this is the z direction. So do the i, j, and k direction. Cool. And then the other thing that I would draw is do this. Do I, j, k, and then repeat it. I, j, k. So when you cross I into j, you get k. And you get a positive k. If you go this direction, it's positive. So if you cross I cross j, that gives you positive k. J cross k gives you positive I. And then k cross I gives you positive j. So it's, and I would write it twice because it kind of loops around. Because you can have k cross I, so that's why k cross I gives you that positive j. And here's the visual of it. If I have I cross j, and i's and j's can look the same. So if I have I cross j, that's the thumb into the k hat. If I have, let's do this one, j cross k, j cross into the k, that's thumb into the positive I direction. If I have k cross I, so k cross I, that's going to be this way, thumbs in the positive j direction. Obviously, we could do the dead opposite. So let's start here. We're going to go I cross k. So we're going to go I cross k. That's going to give negative j. We're going to go k cross j. K cross j, that's going to give me negative I. And we're going to do j cross I. J cross I. So fingers in j, crossed into I. Hell yeah, it's a negative k. All right, booyah. And, let's do k cross k. So let's throw our fingers in k and then move them into k. It's like, well, that's like a jab. We're not sweeping, you know what I mean? So, and then back to our door analogy. A cross product is giving you that leverage. Everything with a cross product is still kind of leveraged base, and maybe that's not 100% true, but, angular momentum, that's leverage base. It's the distance, it's your distance. You have some sort of, like I did this with the baseball analogy. is that I got two baseballs, one coming to home plate and one coming to first, being thrown by two people. And the angular momentum, and then you have a catcher here. And this is at the origin. And I want to know the angular momentum at this origin. This ball has no angular momentum because it's towards the origin. Now this has angular momentum. This ball has a mass, it's got a velocity, and it's traveling in this direction. And it's a distance away. And it's the perpendicular distance that actually matters. So that's the, and it's crazy. I'm so glad to make these videos because it's just a million little aha moments where it's just like, hell yeah, you're gonna be working on. And it's kind of a side note here. It's just kind of fascinating. I kind of just watched just one person's video. Let's not even talk about what discipline it was, but it was a PhD in all the different subjects, and it was kind of going over, you know, the coursework that they did. So they did an undergrad, did a master's, and then did a PhD in a bunch of subjects. But still, it was just still fascinating where it just seemed like if you asked them what the most basic fundamental was, you'd just be in a head-scratching situation. You know what I mean? So that's why I think it's just critical to go over the fundamentals in just 100 different ways. So you never fall into the trap of just memorizing. Because this stuff, I mean, this is the chapter of like instant centers, and at least I can remember to say instant centers, but would I ever want to calculate an instant center? Hell no. And I looked up the proof of instant center, and it is just ghostly, where you actually have to set up something that's like wrong, show that it's wrong, and then just instantly jump to a huge conclusion that just like, well, that must be the instant, you know, it's just like there's no, in 20 years, I'm never going to look at a problem and be like, oh, hell yeah, I know how to do the instant center of this. Not a chance. Absolutely not a chance. And so, but we'll finish this one. This might be a 3 to 4 hour problem, but I'm just, you know, like I said, it's kind of my day off. This is what we do. And it really helps me probably for other videos. Just kind of going over everything. All right, hell yeah. So let's do this cross product. So we can't cross K into K. We can cross J into K, we can cross I into K. And does that make sense? Because right here, we're going to have a velocity component that's going to have a component in the I direction and a component in the Y direction. Isn't that what we're just going to say? So we can cross I into K and J into K. So I cross K, and then whether you know the sign's going to be positive or negative, who the hell cares? I cross K is J of some sort. It's either positive or negative J. So hell yeah. So just looking at this, I can say, well, I have a K over here. I can cross the I into K to get a J. I can cross the J into K to get an I. And those are the two components. I don't care whether they're going to be plus or negative. I just want to know that, hey, at the end of the day, I'm not going to make mistakes, and my tangential velocity is going to have an I component and a J component. And visually, we already see that it has a positive I and a negative K. So let's see how those things work out. So we have... so this is how I do it. I do this. I go 5 times negative 1. So we got 5 times negative 1. And then I have I cross K. Come up here, and I got to go the other direction. So I cross K is going to be a negative. So I got negative 1, and then I cross K is J. Hell yeah, that's how I do it. And you know, we can simplify this already. This is just 5J. Oh, hell no. You know what I mean? Is this... It feels like we want a negative here, and why didn't we get that? Oh, you know, no. Yeah, our position vector. Holy hell, this is going to drive me insane. So I think we have a mistake. So let's, we did I cross K. We're going to get a J hat component. That's going to be a vertical, and the vertical is going to be in the negative direction. The I is going to be positive. Well, let's just do the next one and see. Yeah, and then the omega is this direction. This thing is going that direction. And that's in the negative K direction. And maybe it is this. Maybe tangential velocity is omega cross R. Let me look up the book, because I don't like... This is the first time I've ever... even used an equation, so we actually need to see what the sign convention is on this one. Alright, hell yeah. So I took a break, and I'm glad I did, because it was just like, oh yeah, no duh. It should be just really obvious. So let's take this as our distance vector to P. Cool, so that's a vector. And this is going to be R from the origin to P. And my bad. I was saying like you would do like O/P. Hell no. This is when we talk about relative velocities. And you know what I mean. Let's at least look one up, because I just did it. So they're saying, hey, what's the velocity of C? Well, they're saying the velocity of C, just pretend, well, what are they going to say? They're going to say the velocity of C relative to this point. You know what I mean? So we're just going to say that point is fixed, and we're just going to, damn it. I don't know. But anyway, to find this velocity of C, you actually have to take the velocity of C relative to that point, plus then just the velocity of C. Like those two things are, so yeah, in the example, they do velocity of C is velocity of B plus velocity of C relative to B. Anyway, all right, moving on. Holy hell. But they were saying that we should be able to, so in this case, this thing is rotating this way. This angular speed, the vector, is in the k direction for this example. And they said it should just be real easy. And then so your velocity tangential is going to be tangential. So there's only two ways to cross these. So we have this distance vector r. So, and I'm sorry I drew it at a funny angle. And then we have this angular speed vector, omega. So if we, let's just cross one into the other. We're going to cross omega into r. Yeah, I guess we would do this down into that direction. Yeah, so this is our 90 degrees. And this, yeah, that does point in this direction. So if we go out of the page, directly out of the page, but then curl our fingers down into this direction, hell yeah, we're going to be pointing in the direction of that tangential velocity. Had we done it the other way, you know, like put our fingers down into the page into R, and then curl out of the page, well, look at that. My thumb is going that direction, which is not the direction of tangential velocity. So hell yeah, let's do one more quick example, because if I just want to do this real fast, here's my omega. You know, we're going to be thumbs up that way. That means my vector is coming out of the page. You know what I mean? Like this. So this is my omega vector. I'm going to have a distance vector over to here. I do know my tangential velocity is that. Here's a 90-degree angle. So look at this. I'm going to come out of the page, directly out of the page, and then swing into this R, and hell yeah, we're just right there. And is there, if I go the other way, is it easier? Well, we could also do this. We could say, hey, this direction, this is my position vector, so we're going to say omega comes out of the page, and then we're going to roll it into this R, and oh, this is really awkward. So there you go. So my omega comes out of the page, and then we're going to roll the fingers into R, and my thumb, it's kind of out of the frame, my thumb is down, and that's what we see here. This tangential velocity tangential would be down. So I just love, and they just said, oh, it's like super obvious. Man, textbooks are just brutal. They're just like, so here is, that's the relative motion. And I had to thumb through every page of this, because I just didn't think they would, you know, go across this concept until about halfway through the book. Omega cross R is tangential, is the velocity vector. And they say, these results agree. Using the right-hand rule for the cross product, it is not difficult to see that the directions of the vector in this, you know, right there, are the same as those in equation 16.6a. 16.6a. I don't even know maybe what they're even talking about. But that's all. Like, maybe I just read this wrong. But, like, I think, you know, using your right-hand rule, it should be obvious that, it should not be difficult to see that the omega comes first. It's not R cross omega, it's omega cross R. So hell yeah. So we beat that one to death. But that was just one where it's just like, I don't know. Like, unless you spend some time thinking about that, like, you know, you could just look up that omega cross R is the velocity vector. But I think that's a horrible way to memorize. You're just going to be memorizing like that nonstop, and in 20 years you're not going to know a damn thing. But just knowing, like, even this, if you're not drawing this little guy, like, you know, this is the right-hand rule savior. You know what I mean? You can do any cross product you want. And then you can see how you can't cross K into K. You'd be jabbing it. You can't, you're not moving your fingers. The only way, anytime you move your fingers a little bit, hell yeah, this thumb counts. If you don't move your finger, this thumb is 0. You know what I mean? There is no vector in that direction. And you wouldn't know where to cross it anyway. You could jab your fingers in K, but you could also roll your hand in K, and you just wouldn't know. Like, it's, the second you actually roll your fingers and cross it into something, hell yeah. Then you're gonna get. And that's why we split up a vector into Cartesianal coordinates, because then you are getting perfect 90s. If I cross K into I, hell yeah, I get a positive J. 100%. Like, the entire component of this K crossed into an I, or I guess in this case, the entire component of the I crossed into K. That's where I just get to multiply that 5 times negative 1. Alright, but let's do this right, because we need to do omega cross R. And so that's going to be, let's burn this one out. Alright, booyah. So we're going to have negative 1 k hat crossed with 5i, 5j minus 5k. Alright, hell yeah. Now, can we just do that? Maybe we don't even, well, no, let's write it out. So just the way that I do it, I go negative 1. So we're going to cross I into k. We can do that. No, k into I. So negative 1 times 5, k crossed I. Then just say ijk, ijk. Yeah, this is going to be positive. Yep, hell yeah. So we're going to get positive 1. You could just do positive 1. I don't know, or don't do anything, or, you know, but I think that crosses your I's and stuff. And then k cross I is j hat. It has to be the opposite, right? It has to be, you know, if you're crossing k into I, you must get j. You can't get k or you can't get I. Got it. Alright, so hell yeah, k cross j. So we're going to do that one. I still do a plus. I'm going to do negative 1, 5, k cross j, I, j, k, I. So it goes ki, but this is kj. It's going the opposite way. And going back up to here, k cross j, that's going the opposite way. It's negative. So we're going to go negative 1. K cross j is I hat. Booyah. And then k cross k is 0 hat. You could do it. You could go negative 1 times negative 5. And you'd be like k cross k. Well, that's 0. You know what I mean? So hell yeah, you have 0, and there's no real direction on that either. So there you go. Okay, booyah. So we're gonna have negative 5j hat, and then we're gonna have 5i hat. So we're gonna have 5i hat minus 5j hat. Now, does that feel about right? Oh man, I feel like I don't think so. Oh, and we messed it up anyway. Damn it. My bad. No, I don't think we messed it up. No, we didn't mess it up at all. I just messed up my drawing. I said that this was 5 inches. This can no longer be 5 inches. Like, this dimension was 5 inches. This was 5 inches. So this diagonal was 5 times the square root of 2. this distance has to be 7.07. So my bad about that. I don't know where I got, kind of just discombobulated. And I'm sorry just to do an example problem that really doesn't even have a good picture. But hell yeah. So this lever arm would be 7.7 inches, and then the components would be 5 inches per second, 5 inches per second. That's kind of what we got. Hell yeah. All right, I think we just got to move on. I at some point need to finish this. Let me print out some more sheets, and I think we're on our way to just maybe solving this problem because I got to move on. All right, hell yeah, we got some more printouts. And so what we're going to do now is probably what I should have done at the very beginning. We have enough intro of kind of knowing what's going on. So the first thing that I do with problems is like, can you just guess? It's because we want to know the velocity of P. We want to know the velocity of this slider. We also want to know the acceleration of this slider. So now, I mean, we know that the slider is moving this direction at 120 millimeters per second, or 0.12 meters per second. And hell yeah, that might be pretty representative. But we know that this thing is rotating and it's a distance away. So let's just guess this distance. If this is 200, I don't know, maybe this is 300. 300 millimeters. Cool. And then we have angular speed of 0.8 radians per second. Like we said, radians times radius, omega times radius is tangential velocity. So this is going to give us a tangential velocity, and it's going to be in the perpendicular direction of 300 times 0.8. That's about 300. You know what I mean? Or like 0.3. So yeah, there you go. So, and maybe just a little bit less. Maybe it's 0.24. So booyah. And so we have 0.2 that way, 0.24 that way. And so if we kind of add those vectors up, and this is another good thing to do, is just like, hey, let's just say this is 0.12, and then we're going to double this. That's 0.24, and how do you do this? Yeah, and then we're going to add these vectors together, and then booyah. So now if this is 0.24, this is 0.12, maybe this is 0.32. You know what I mean? So there you go. So I'm just going to guess an average velocity of 320 millimeters per second. That's just a guess. I mean, it gets you in the ballpark. Like, who cares, right? And then the angular acceleration. That, oh man, maybe I don't know how to guess. So let's hold off on this one. But what I want to do is also kind of figure out another way to get the velocity. You know what I mean? What is, and this might actually help us get the acceleration as well. Okay, so because the other thing that we can do is we can say, hey, this is going 45 degrees every second. So in 1 second, this point is going to be right here, and then in 1 second, this thing's traveling about that far. So it's going to be, this point's going to be right there, but the slider is going to be right there. Okay, yeah, never really thought about that. Yeah, let's just use that. So in 1 second, it's going to go 45. This point on the rod is going to be right there, but this slider is going to travel another. It's going to go 120. We're saying this is about 100. So if we're going to be at a 45, we're going to go about right there. Okay, hell yeah. And now let's just draw this in. Even though it makes this path, we're just going to say it's kind of linear. So in 1 second, we're going this distance. If this is 200, so maybe from this perspective, it only looks like it's going less than 250 millimeters per second. So those are our two guesses. Yeah, it's kind of interesting. I was going to take this another direction, but no, I messed up on the way that I was thinking. I thought we could actually get this thing up here, and then it would be... But no, this thing's going to slide off due to its motion. I mean, and we even know what a quarter circle is. You know, should we do that again? What's the circumference? Well, what's the angle? The angle is going to be 2 pi divided by 4. It's going to be 1/4 of a full circle. So this is going to be the angle in radians. Radians times the radius of 200 millimeters is arc length. So that's what I did there. Angle in radians times radius is arc length. Might as well use the equations that were, you know what I mean, and then back it up. You know, if we go back to 8th grade, pi d is our circumference, and so that's going to be pi times 400 millimeters. That's the circumference, and then we're going to divide by 4 to get half a circle. So we got pi divided by 4 times 200, which is essentially pi times 100. And then right here, we're going to have 400 divided by 4 is 100 pi. So hell yeah. So arc length is pi times 100 millimeters, which is 314.15, you know, blah, 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 right? Millimeters. Okay, hell yeah. And if this thing's going 120, so yeah, we can do that. So we can figure out how many seconds it's going to take for this thing to just leave the rod. So we're going to go 100 times pi divided by 120. And it's in 2 seconds, 2.61 seconds, it's going to be right there. So we can do another calculation, but let's see. But the other part of this problem that we're not taking into consideration is that this thing is slowing down. And maybe I'm just don't know a good way to actually take that into consideration yet. So hell yeah. So now we're actually going to start the problem like I should have. You know what I mean? If I just got to it, this is how I was going to start the problem. Alright, hell yeah. So what we want to do is we want to take a very small snippet in time. I start with 1,000th of a second. 10,000th of a second is going to be too hard. I'm actually going to store that in my calculator as alpha t. Booyah. Alright, so now what we're going to do is we're going to have, you know, the position at time 0. Cool, it's just right there. And, you know, if this is our coordinate, we can actually get position on this point. It's going to be over 200 in the I direction, and then, yeah, let's do that. So we're going to get point P naught is going to be, you know what I mean? Like, yeah, so what's the position on that? That's going to be 200I minus 200J. Hell yeah, and that's going to be in millimeters. Okay, now we're going to run it for 1,000th of a second. This thing is going to be traveling along this rod, but not very much. It's going to be the speed. Let's do factor label. Millimeters per second times 1,000th of a second. Seconds cancel, and this is the distance we're traveling. And it's probably good to, like, you know what I mean, how did that work? Because velocity is change in position, change in time. So so if we have velocity times change in time, that's going to give us dx, dt. I don't even know what I'm doing, but obviously you're going to get the change in position. Hell yeah. Alright, so yeah, that's going to be the change in position, and we're only going to go, this is going to go 0.12 millimeters. Okay, so hell yeah, so this is going to go 0.12 millimeters along this rod, but this rod is, well, and now the rod is doing two things. So one is that we can just neglect acceleration, but I don't think we should. I think we should be able to do this all in one go, even though it's tricky. It's kind of going to be the trickiest part, is because at this instant, we do have, yeah. Because angular speed is change in angle, change in time. This is how much the angle is changing for every change in time. We know that every point on here is actually going to change the same angle. I think is that provable? You know what I mean? Even this point right here, Does that make sense? It doesn't feel right for that point, you know what I mean? But I guess every point on here, like if, well, let's do that. If, because this point's going to be kind of in this direction. Let's take this all the way up to 90, you know what I mean? Cool. Then this is going to be 90 right there, you know what I mean? And hell yeah. So, yeah, every point on here is going to change the same angle. That's fascinating with the rigid body. That's probably what I'm most fascinated about learning from this problem. Oh, man, this seems brutal. But, okay, so what do we need to do? Yeah, the change in angle. Okay, sweet. So we know that if we run this, if this is constant, we're going to have 0.8 radians per second times 1,000th of a second. And so we're going to have so we're going to do this 3 decimal places. So 1, 2, 3. This is how many radians, and this is going to be time in seconds. So this is how many radians we're rotating. Oh yeah, no duh. Okay, yeah. So it's fascinating. Yeah, let's throw an angle on this. So we're gonna call this theta, and this is gonna be theta naught. Cool. So then we're actually gonna get theta at 1. Yeah, no duh. Okay, so that's gonna be the trick. You know, because what we're doing is just basic trigonometry. So now this angle. So theta naught's 45. So theta naught is totally 45 degrees. I'm going to do that in radians. So that's going to be 45 degrees. We're going to go 360 degrees downstairs, 2 pi radians upstairs. Hell yeah. So 45 times 2 pi divided by 360. Is that radians and 40? Yeah, because 1 radian is 60, so 0.78. I've never done 45 degrees. Oh yeah, and we said it's really close to 0.8, but it's actually 0.785. That's what threw me for a loop, because 0.785 radians is equal to 45 degrees. It just didn't look like 0.8. You know what I mean? That's what we were saying though. All right, hell yeah, and sweet. And we're totally gonna, we gotta save these things into our calculator. I'm gonna store this as A. And I'm getting into the habit of just like, hey, we only got 27 letters in this TI-83 plus a couple characters. And, yeah, that sucks. We need to have more storage capacity for answers. But you might as well start with A and go A to Z. That's my new game plan. Okay, so this angle gets reduced because if this thing's rotating out, this angle's going to shrink. So theta is going to be theta naught minus omega times that change in t. Sweet. Change in t is, we stored this as value t. Hell yeah. And so this is going to be a omega. I'm cool with just not storing this, but we got omega times t. So that's what that looks like. So we got alpha a minus 0.8 alpha t. And that's so this number is different though, and we're going to store this as alpha b is 0.784. Cool. It's a little bit less. We're going to store that as alpha b. We're going to run it for another 1,000th of a second. All right, hell yeah. Because if you're just trying to find velocity, we're done. But if you're trying to find acceleration, you got to run this twice. Make a small change in t, run it twice. And now we're going to take theta 1 minus omega t. Or you could have done theta naught minus 2 times omega t. But actually, we got to hold on here, because we're going to have this is driving me crazy. How do we incorporate this angular acceleration? Because I think if we just take such a small snippet, I don't think this angular acceleration does it feel like it goes away? I don't think so. I think you always have to take it into consideration. And so we haven't, we just considered that there was no angular acceleration. But let's do the problem without taking this in, because I just know I'm going to make a mistake. Okay, hell yeah. So this is going to be b omega t. So we got alpha b minus 0.8 alpha t. And yep, this is going to be 0.78. I'm just going to call it 3. I'm not going to throw 4 digits on it. I just want to show you that these are reducing. Cool. We're going to store that as C. Alright, hell yeah. So now, what do we know? Holy hell. Because I want to do this with position alone. So we know that in 1 second, let's just say, hey, this gets reduced and we're now up here. So this, not the slider, but the position on the rod moves to right there. And oh damn it, how do we figure that one out? Alright, hell yeah, took a little break, and oh hell no, you know what I mean? I think I messed up. I don't think I can do this one with this setup. You know, some of these problems you can actually just figure out where the location is going to be, you know what I mean? And then if you know the change in distance for that time period, you get the velocity. And if here's the position 1, here's the position 2, you actually know the direction. You know what I mean, change in your x, change in your y, and you know that you had a change in t. So change in x divided by change in t is that component. But yeah, it's just kind of interesting that, like, I don't know where these points are going to be, because this is a curved surface, and it's just like, whoa, I totally apologize. But maybe I'll come back to this one, you know, to be like, well, couldn't I have done it? Because I gotta treat this like it's a full solid. If I do that and I treat it like it's a semicircle, you could even treat it like a circle. You know what I mean? But this point will for sure travel also in its circle, you know, around there. And then so yeah, I need to incorporate all these reference points in. And I guess I think it would just be a lot harder. For whatever reason, I'm not seeing it. But I do like the geometry challenge. But I think we have to move on. And it's just fascinating where I think vectors will be king. So we're going to have, you know what I mean? So we have our k hat direction. So we have I, j hat, and then this is the z direction. Cool. I guess I'll do that. And so we do have, this is omega AB, cool, and that's going to be 0.8. This is in the k hat direction. Our acceleration is going to be in the other direction. This is going to be alpha AB. That's going to be 0.5, negative 0.5 k hat. And hell yeah, so now I think we can just kind of solve this problem like we should. We know that, and now I'm just wanting to get done, but this is the most important part, is if we have something traveling in a circle, because we're gonna neglect that this is spinning, you know what I mean? And this is where you get into the relative velocity. The first thing you want to know is, like, well, forget all this, but this point is going around in a circle, and so you do have an acceleration, a normal acceleration. And the equation for this, and this is where I would just want to actually derive it, but we have too much going on, you know what I mean, where I just, like, I physically can't, yeah, but I don't know, I'm just kind of about done. But we know the equation, because then you're just guessing what the equation is, which is kind of sucky. But it's r omega squared. That is the acceleration. And if we do F equals ma, and if we have the force required, because you would need, this is a mass, you would need to put a force on this in the normal direction to maintain this circular path. That's why we call this a centripetal force. Even though the force is centrifugal, like it's trying to push this chunk of mass outward, you need to have some sort, sometimes you would have a string, so you would get tension in a string, and that's going to be the force towards the center, the normal force. So yeah, so if you want the force normal, that's mass, and then r omega squared. So this is the acceleration. Yeah, and that's the normal. So here's your r omega squared. So mass times r omega squared makes that F equals ma. I'll check out. But anyway, so r omega squared, we have that. And we know what direction it's going to be. This is going to be in the j direction. So we have j direction. That's going to be positive. Okay, hell yeah. So we can just do that. This is going to be 200 millimeters times 0.8 radians per second squared, which is going to be, so 8 times 8 is 64, and then you'd go booyah. So it's going to be 0.64. So this is going to be 0.64 times 200. I don't know what 0.64 times 200 is, but I do know what 64 times 2. Maybe I don't even know that, but I do know 120 is 60 times 2. So it's going to be 128. And again, we got to start moving some decimals. 200 times 0.64 is the same thing. Let's move this decimal. That's the same thing as 2 times 64. So I think we get that. And hell yeah, now we're just 128. So that is our answer. We got 128 millimeters per second squared. That's going to be our acceleration. Hell yeah. So we have the acceleration normal. All right, so now we're just doing it like normal, you know what I mean? And so, yeah. Oh, and that's the other thing. Yeah, this is angular acceleration. This is in radians per second squared. You know what I mean? What the hell's a radian? That's where we have to go back to, hey, angle times radius is arc length. Angular speed in radians per second. Radians per second times radius is tangential velocity. And then angular speed in radians per second squared times radius is tangential acceleration. And so if we go to this point, we're going to have an acceleration tangential. And then this is going to be equal to this alpha. This is going to be 0.5 radians per second squared times the radius. This distance is going to be, and we already did this, 200, it's going to be 200 millimeters times the square root of 2. You know what I mean? Just because we already went over that whole thing. This is just kind of like a 1.5. It's 1.4142. You know what I mean? Hell yeah. Multiple. Cool. And that's going to be the tangential acceleration. And we know this is going to be a 45-degree angle. So sweet. So this is going to be the magnitude of this acceleration. You know what I mean? So that's going to be the magnitude of that acceleration. But the actual vector is going to be that magnitude. It's at a 45, so we're going to divide this by the square root of 2, and then we're going to get the components. So instead of taking this times the square root of 2 and then dividing by the square root of 2, we just know the components are going to be this. So we have, instead of 0.5 times 200, I'm going to do 5 times 20. I don't know what 5 times 20 is, but I do know what 5 times 10 is. 5 times 2 is 10, so it's going to be 100. So hell yeah. So this is going to be 100 millimeters. No. This is going to be 100, and we're going to go in the I hat, plus 100 in the J hat. That's the components of that. 100 in the j hat, and that's going to be millimeters per second squared. That is acceleration. There's no, angular acceleration is kind of a dimensionless per second squared. You know what I mean? So you have to multiply it by something to actually get something normal. See how that works out? So radians per second is a ghostly number until you multiply by meters, to get meters per second. Because radians is dimensionless. It's an angle. You know what I mean? But it's still kind of a dimensionless unit. All right. Hell yeah. I feel like I'm on a roll and I'm actually kind of learning how to just do the problem the right way. Now, I have not looked up how to do this solution, and I have not done similar problems like these. Like I said, 20 years ago, probably did stuff like this. But not really. I squeaked through this class without... Man, I didn't learn anything. I don't know. I think I had a good teacher. Well, it just is what it is. You can only learn so much. There's only so many seconds in a day. All right. Okay, so what are we doing now? So we have the two components. That's it. That's the only thing that's causing this to accelerate. Because this velocity isn't changing. So it's just this normal acceleration. So if we add these vectors together, this is j hat. I don't even know why I didn't do that. So hell yeah. And so hell yeah. So our acceleration total, acceleration of p is going to be adding these up. And so we're going to have 100 I hat plus, these add up to 228 j hat millimeters per second squared. And again, this is a triangle. It's a triangle that's 100, and then it's a triangle that's 228. You know what I mean? So, hey, what's the hypotenuse here? You know what I mean? Because what is the actual magnitude of this? Well, just take the bigger number times 1.5. So we got 228 times 1.5. Now, that's probably wrong. If this is half, you don't go down too much. I would say 1.25. 1.25 times 228. You know what I mean? So I'm gonna guess the average. I'm gonna guess we're about 290. All right, so let's do it. So we would be 100 squared plus 228 squared, square root of that, and we get 248. Oh, so I was definitely off. Yeah, it wasn't much. Oh, that's interesting. Yeah, the multiple goes to almost 1.1. Only if these two things are close. I mean, if this thing is hardly anything, yeah, then I totally forgot about that. Yeah. The multiply by 1.5 is only if these two are fairly big. But if this is less than that half, so it's like 228 times 1.15. And that's still an overshot. So 228 times 1.1, holy Toledo, look at that. So hell yeah, this is our answer. And then we want to do this divided by 228. Yeah, and it's a 1.1. Yeah, that's I always do that just to kind of feel it out. But look at this. If we did 100 here and then 228 there, if this is 228, look at this. These are about the same. When you swing this up, you only get just a little bit more. And that's going to be that 248. Okay, hell yeah. So we see that the acceleration is going to be 240, looks like 249.0 millimeters per second squared. That's going to be the acceleration, hopefully. All right, now let's do the velocity, because we know if this is the omega, we have a tangential velocity here. Velocity tangential is going to be, this times the distance. The distance is, so we got 0.8 times 200 square root of 2. Same thing. That's going to be the magnitude of this, but we're going to have components that are going to be x and y, so we're going to have to divide by the square root of 2. So hell yeah, we're just going to have 0.8 times 200. Don't know what that is, but I do know maybe what 8 times 20 is. And maybe I don't. I do know what 8 times 2 is. It's 16, so it's 160. So for our velocity component, we're going to have 160 I hat plus 160 j hat. This is due to this angular speed. But we're also having a velocity this way at this instantaneous moment. So we're also going to have I mean, this is the velocity due to the omega. We have a velocity of 120. This is in the I direction due to just whatever, you know what I mean, just a velocity of this slider relative to the rod AB. That's where this thing comes, that means relative. Okay, hell yeah. Let's add these together so we can just find the velocity vector of P. We're going to have 60 goes to 80, so we got 280I plus 160J. Well, let's try to do it again, you know what I mean? Hey, yeah, this looks like about half, so we're going to have like 280 times 1.12. I don't know, maybe it's 313. Let's see if we're pretty close. 280 squared plus 160 squared, square root of that, and we undershot, so we have a... the magnitude of this is 322.5 millimeters per second. And man, I just want to be done with this video. Like, obviously, there's a lot more that we could kind of, I don't know even what I'm saying. Alright, I don't even know where we were on this one, so let's look this up. Alright, hell yeah, I'm glad. We got the velocity right, we got the acceleration wrong, and, you know, my bad, because this vector is going the other direction. We're slowing down, so this is going this way. And so, and then let's just double check. So this acceleration is going to be the radius times omega squared. And so I think we have that right. Let's just, I think we maybe messed this up. 0.8 squared times this radius. This radius is going to be 200 and then square root of 2. All right, so hell yeah. So we're going to store that as alpha A. And see, I didn't get that right at all. I don't know what the hell I was thinking. So this is 181. Why couldn't we do that? I don't know why we messed that up. So we have 64 times 2. That's going to be 128. Oh, holy hell. You know what I mean? I didn't... wait, what? Oh yeah, this distance is not 200 at all. It's 200 the square root of 2. So yeah, my bad there. Yeah, so this is 181. Cool, and that's going to be in this direction. It's the J direction. It's the up direction. Now this has two components, and it's this 0.5 times the radius. So we're going to have 0.5 times 200 times the square root of 2. But this is going to give us the full magnitude. It's a 45, and then so to get the components, we're going to take the hypotenuse, that bigger number, and then divide by the square root of 2 to get one of these sides. So we're just going to drop that out, and then hell yeah, this is the same thing as 5 times 20, and then we have 5 times 2 is 10, so this is 100. And then, so this is going to be 100 in the negative, so it's negative 100I, and then minus 100J. So that's the direction. This is going to be an acceleration that way of 181 in the J direction. So we're still going to have an acceleration of P of negative 100I, but then we're going to have a positive 81. Cool. And if we do this, and I swear I'm not even getting this right. We should just look at the book because we totally hosed this, and I don't know what we're doing wrong. So let's yeah, no, we got the 181, but this is 141. So I don't know why we're striking. No, that's right. Yeah, 141. No, we're good there, and it's got a component of yeah. If this is 141.142, this is it's 100 that way, 100 that way. So we're good on that. Wait, is there more acceleration? They're saying this has an acceleration of 72, so that's where we're messed up. Oh, plus the acceleration of holy hell. The acceleration of point C. Where is C? I don't know where they're getting this. Alright, I gotta take a look at this. Alright, hell yeah. So we're hopefully the home stretch. man. And yeah, this one kicked my butt, but it's kind of interesting. I'm glad I just went for it, you know what I mean, and didn't look at the problem, because then once I did, like, booyah, everything just kind of clicks into place. We have a lot of relative motions. So it's like this is the one thing I can think of. Like if you have something that's spinning, and then here's your point P, and this is like spinning this way. Let's say it's spinning 1 radian per second. In 1 second, this point P would be right up there. But now we're going to say this is a slider, and for whatever reason, it's on a track, and this slider is moving with a velocity well, let's say this is 1 meter radius, and so what's this? What's this distance? This distance is 2 pi times 1, so that'd be 2 pi. No, what is this distance? Holy hell. Oh, this is tripping me out. This distance is just 1. Yeah, no duh. It's just 1. It's like 1 meter. So yeah, so that was wiggy. So yeah, let's say the velocity is just 1 meter per second. So in 1 second, we have an angular acceleration of 1 radian per second. So in 1 second, it's going to go up here because it's going to do 1 radian. And that's going to travel 1 meter up. But we're saying this slider is also just traveling 1 meter per second down. So theoretically, it's just like stayed put. But if we so yeah, let's do it, even though I drew it hella small. If we said that this is rotating up, that part, it's going to have a normal acceleration. That acceleration is going to be r omega squared. So that's just going to be 1. Cool. And that acceleration is going to be, well, let's get, this is going to be the j hat direction. This is going to be the I hat. So we have negative 1 I hat for our normal acceleration that way. Hell yeah. Now we're going to see what type of acceleration we have on this. Because pretend like this isn't moving. Now this is moving with a tangential velocity this way. Okay, hell yeah. And so we know that if we're moving with a tangential velocity around a circle, we have a normal acceleration. And that's going to be r omega squared. So we're going to have, that's the other thing, is if we do omega times radius is tangential velocity. So this r omega squared, you could solve for omega right here, so that's VTR. So omega squared is v squared r squared. And then v squared r squared times r is going to be, so omega squared r is going to be v squared r squared times r. That's going to be v squared divided by r. Hell yeah. So if we do that, so this is going to be v squared. It's going to be 1 squared is 1 divided by 1. So we still have 1. And that tangential velocity is, oh, this is tripping me out. If this is, oh, weird. It's weird that those don't cancel, and I don't know why. I thought I was going to make an example where, yeah, if this is moving up this way, you're going to have a tangential velocity towards the center. If it's moving down, oh, that's weird. You're going to have the same tangential velocity towards the center, so it's still going to be negative 1I. Huh. Negative 1I. But yeah, those wouldn't be additive. I mean, obviously there is no acceleration because it's not moving. Alright, hell yeah. We just got to move on. Because it's talking about Coriolis, relative, I have no idea. So the way that we got the velocity right, I don't know why, I guess. But the way I was going to do the acceleration, kind of same thing. If this has a velocity around this circle, we have an acceleration normal. That's going to be r omega squared. The radius right here is 200. So we're going to have 200 times 0.8 squared. And let's just do everything in our calculator so we don't make any mistakes. Okay, that's going to be 128. That's going to be in the j hat. Alright, hopefully that's right. Damn. And then, what else? Now, this is also rotating oh, no, this is slowing down, so we have an angular acceleration. Yeah, so we have a, and it's going this way. So we have an acceleration tangential. We also have an acceleration normal. That's the only other part that I totally forgot, because this thing is spinning. This point is spinning about this, so we are going to have a velocity. Like, we do have a tangential velocity. And because we have a tangential velocity, we have a normal acceleration. That's going to be r omega squared. So this one is going to be, the radius is going to be 200 square root 2. And then omega squared, yeah, I'm chill with that. It's just going to be this 0.8. And this is hella wrong. What was I even doing? Yeah, holy hell. No, this is absolute garbage, because we have omega times radius is velocity. Yes, normal acceleration is omega squared, but if we only have a velocity, if that's all we know, we don't know what the angular acceleration is, but we could figure it out. If we know the normal acceleration, omega r, we have this equation. We could just solve for omega. Well, that's going to be velocity times radius. So let's do that. We have a velocity of 120, divide a radius of 200, and that's going to be 120 divided by 200. Well, that was probably smart. You know what I mean? So this thing is moving around this circle at 0.6 radians per second, and now we can throw it in here. So we're going to have 200, and then we're going to do 0.6 squared. Yeah, we were just all sorts of off on this, but that's the story of my life, so... Alright, so we got 72. And I don't know if any of this jives with the book, but we're going to have 72 in the j-hat. And that's going to be positive. Hell yeah, got that one. Okay, so now let's do this. We are going to have a velocity. The velocity of this is, well, yeah. Let's do it in those, man. Let's say, omega times radius is something normal, and therefore, and what we have is this equation that says r omega squared is acceleration normal, and so, but we want it in terms of velocity, so we're going to make this in terms of, and then shove it in here, so we have r v r squared. That's going to be r v squared r squared, which is v squared r. Hell yeah. And I guess a lot of people just memorize this one. I choose not to, but I don't know why. This one just looks like I can memorize it. This one looks like I'll just mess it up, but probably not. Okay, hell yeah. So now we just need to know the velocity here. The velocity due to this is, well, velocity tangential is omega times r, something, radians times radius. That's going to be 0.8 times 200 times the square root of 2. Alright, so that's what we have here. We're going to square this and then divide it by the radius. Okay, so that is kind of redundant, because holy hell, that was, yeah. No, maybe we want this all in terms of, what? Yeah, no, we know, yeah, I don't know what the hell I was thinking. Yeah, we know this just in terms of omega, so we're going to go r omega squared on this to get this normal acceleration. Wow, this is just a learning day. Okay, and then, yeah, so we got 200 square root of 2. This is the distance. The omega is 0.8, and we're going to do 0.8 squared. And hell yeah. Cool. But that's going to be in this direction. It's going to be a 45. So if we want the components, we're going to divide by the square root of 2. So those can just cancel out. And we're going to have 200 times 0.8 squared. And we're going to have negative 128i plus 128j. So that is the normal acceleration. The normal acceleration of this one was in the positive j. So that's our two accelerations. Do we have any more accelerations? Man, I don't even know. So this velocity causes, oh yeah, and then you just have the acceleration tangential, which is angular acceleration times r. There's just so many problems that don't have a slowdown of speed. Usually speed is constant. Angular speed is constant. Not on this one. It's slowing down in this direction. So we're going to have radians times radius, even though it's radians per second squared. Radians per second squared times radius is something normal. That's acceleration tangential. So we're going to have 0.5 times this radius, which is 200 square root 2. This is the tangential, but it does have two components. And again, we're going to divide by the square root of 2 to find those components. And then, hell yeah, it's half of 200. Holy, so what the hell was I doing? I was going 5 times 20. That is crazy. 0.5 is half. I just don't know why I didn't see that. So it's 100, because I just looked in the book. And then we're going to have 100 in this negative. So we got negative 100 in the I hat, and then we have negative 100 in the j hat. Sweet. So here's our 3. Man, I'm gonna pause because if I didn't get these right. So 72, perfect, and then we have 192. I don't know where they get this Coriolis effect. That's absolute insanity. Let's just add these up and see what we're missing. So our I hat terms, we're gonna have negative 228 in the I hat. Our j hat terms, okay, hell yeah. So this 100 will cancel that 100, so we have 72 plus 28. Okay, 8, 7 and 2 is 9, 8 and 2 is 100, so we're going to have plus 100j. And hell yeah, and so we're going to have 228 squared plus 100 squared, square root of this is 248.9. I feel like that's wrong. I feel like they have a Coriolis effect. They have 228 and then 292. Where are they? Where are they? This Coriolis acceleration. Oh, that's in 2 omega. Oh, that's tripping me out, man. The acceleration of p relative to AB has only a normal component because v is constant. Got that. Because the normal component of the relative acceleration is toward the center of the curvature of the path, we find that it's just in the j hat. The Coriolis acceleration. Whew, man. Because that really bumps the j hat up. Because we're going to have a Coriolis acceleration of... oh, and this should have been 100. Yeah, so we're going to have a Coriolis, so it's going to boost up 229. So this should be 229. We need a 229. We should have a Coriolis effect of 129. Is that what they're saying? 192. Oh, we're just getting this hella wrong. 292, 192. Or I'm gonna look up what the hell the Coriolis acceleration is. That sounds made up. But anyway. All right, hell yeah. So we got to be done with this problem, and you know what I mean. Kind of just kind of one of those trash videos. But this is good because this is the learning process, and I ain't gonna solve the world's problems tonight. But I guess I understand where this Coriolis effect comes from. In the intro chapters of rotational, of a rectilinear, no, I'm just making up words, but where you have a particle that moves in a curved path, curvilinear? Yeah, curvilinear coordinates. This has every acceleration, you know what I mean, not these basic equations, but once you get into all of them, you get them all, you know what I mean? So, and then one of them is the Coriolis acceleration. So again, we're not going to go over it, but I get where it comes from. It's like this. Let's say you're, so here is the North Pole, South Pole is, and then we're rotating. I forget which direction the Earth rotates, but we can figure it out. We should do this every time until it sticks. So here's the North Pole. You know, here's Montana where I live. New York is over here. You got the big, and then so they see the sun first. So I'm just going to put the sun is fixed in the sky. You know what I mean? Booyah. And then so we must be rotating this way. So on a down view, we're going to be rotating. So if this is north, this is Montana. East is over here. Skyscrapers. Sun is fixed. Hell yeah, we're rotating this direction. Yeah, I was going to say this because it's just easier to draw that way. Okay, hell yeah. So we have the North Pole, and so we're rotating this way. And let's say you get into an elevator of a really big building, and you're moving up quickly. Okay. One of the things that's very similar to our problem is, hey, we have this velocity that's constant that's going around in a circle. So yes, if you just stay on this floor, you're going to go constantly around in a circle. But if you move up quickly to this floor, look at this. Or there's just a person on the next floor up, they are traveling at a faster speed. So the fact that you're traveling at a slower speed, velocity, and this person's traveling at a faster speed, but you're moving up this elevator, so in 1 second you are going to be traveling this speed. But there's nothing to this is really cool. All right, hell yeah. Yeah, I should make more videos. So I am. Anytime I'm going to do these problems, you know, it's worth it to, what is normal accelerate? You know what I mean? Like, it's because normal acceleration, if you're going around a circle, is you're right here, you are literally going this way. You have no velocity. Your velocity towards the radius is 0, but at some point you're over here. And you should have been right here, but you went this direction, you know. And it's not like you went up, but you had a constant velocity towards the center. And so that's equatable. But you don't have any velocity towards the center. Here you must have had velocity towards the center. So you had a change in velocity towards the center. That's the definition of acceleration. Change in velocity, change in time. Whoa. Oh, and this is the... yeah, get the big juicy pen. Same thing here, kinda, you know what I mean? Hey, look at this. Your velocity should be constant because you're just constantly going around the Earth, but you chose to go onto a fast elevator and you moved up to a point up here where now your velocity is higher. So look at this. Like, and this is where you have to have relative reference frames. I wish I didn't scribble all this, but when you're in an elevator, you don't feel, okay, the elevator stopped. You don't feel like you're rotating around the Earth, but you are. So, but it doesn't feel that way. It just feels like you're stopped. And then all of a sudden it feels like you're going, you have a velocity this way. So sure, we get it. You do have a velocity that way. And at this point you have no, oh, this is where it gets into relative velocity. You know what I mean? Because it's not, it's this change in velocity. So this velocity is hella. This is like 1,000 meters per second, and this velocity is going to be like 1,000. No. It's 1,000 miles per hour. But let's say it's let's say you're going 455 meters per second. That's like tangential speed of the Earth. I don't know if it's 500, but anyway, you get the idea. And right here, you're going to be going 460 meters per second. So relative, you could say that you have 0 velocity in this direction, but when you pop up here, hell yeah, you got 5 meters per second. Therefore, you have an acceleration tangential. You have an acceleration tangential that's going to be the difference between those. And, hell yeah. And I can't prove it, but it says, hey, look at this. It just says, hey, use a stupid equation. That's like the worst. When, you know, they don't even explain it. So we're going to say this acceleration due to the Coriolis effect is a tangential acceleration. And it's going to be 2 omega. We can do it upright, though. And then cross product with the velocity relative. It's the velocity of P relative to the body. So hell yeah, let's do it. Do we have another sheet of paper? For sure. So Coriolis acceleration is 2 times omega cross product with the velocity of P, but it's relative to the body. They do a squiggly R, cursed if R. So the body is this. You know, we're going to say, hey, this thing, this little slice, it doesn't matter if it's, you know, it could be a full circle. It doesn't really matter. Anyway, the velocity relative to this body, that's why you get rid of this, is just that direction. Sweet. So we have 120 I hat. And then we have this body is rotating, though. You know what I mean? And it's just fascinating that the fact that the body is rotating about this fixed point is the same thing as this. I don't know. That's what I don't get. Well, it's because these problems all they use a fixed point. You know what I mean? So maybe there's more to that. Huh. Coriolis acceleration. Oh, yeah. Yeah, there's now, oh man. Yeah, anyway, these problems have like two origins. One is fixed and it can be outside of the body. One is on the body right there. And we just got to move on. But anyway, so they use this and it's going to be in the k-hat direction. So we have 2 times 0.8 k-hat times 120. I'm just going to say this is 12 and this is 8 times 2. So we have 16 times 12. K-hat times I-hat, we're going to go I, J, K, I. That's close enough. And then so we got K cross I. That's positive, so we're going to have a J-hat acceleration. So we're going to have positive J-hat. So our positive, our positive 10 boosts up to another 192. So we're going to have 292 J-hat. So we're going to have negative 228 I-hat plus 222 J-hat, and no one really cares. Holy Toledo. But I do want to make more videos on this topic. This is just kind of like a learning day. But we can do this. You know, I made the video where you FOIL this. This is 10 plus 6, and this is 10 plus 2. You can do this into your head. So obviously it's going to be 100. So you're going to have 100, and then you're going to have 60, and then 20. So 60 and 20 is 80 plus 100. That's 180. 16 times 2 is another 10 and 2. So 192. So sweet, 192. That FOIL method is really going to be useful for low digit numbers. Now if I have like 86 times 29, this one sucks. You know what I mean? Because I have like, I have a, well, I could do this. I could still do this fast. I would just have to say, this is 80 times 20. That's going to be, 8 times 2 is 16, so it's 1600. We're going to have 80 times 8 times 9. See, or no, yeah. It's 8 times 9 plus another 0. It's 80 times 9. So 8 times 9 is 72 plus that 0. 2 times 8 times 9. So now we're going to have 2 times 6. 20 times 6. 2 times 6 is 120. There you go. And then 6 times 9 is 54. Whew. So I don't know if that probably didn't seem easier. 5, 6, 7, 8. No. 5 plus 4 is 9. And then 8. No. 8 plus 6 is, that's a tough one. 8 plus 6 is 14. And we have 2494. Now if we did this, I think that was faster, like the FOIL method, because here, oh, this is just painful. No one likes to do it this way. 72, 77, and then you're still going to have to add numbers. Here you added 4 easy numbers. This you just have to grunt it out. So we have 12, 16, 17, and yeah, I make hella mistakes on this. Sweet, 2494. Yeah, same number. Alright, hell yeah. So we did it. We got that 192. Man, I'm done. I'm thoroughly done. But I think, and maybe I'm totally wrong, maybe the Coriolis acceleration isn't this, but no, it is, because I looked at videos. It's as if you have a circle, you know what I mean, and then you're moving along it. But this is a better explanation. And what this shows is you're going to have a tangential acceleration, F equals ma. So you're going to have, if you have a tangential acceleration, you must have a force. You're a mass, you must have had a force that pushed you in that tangential way. And and this is the back of the elevator that you're putting your back to. As you're going up, if you're spinning in this direction, the elevator will feel like you're being pushed. You know what I mean? You'll feel a pressure on your back. Now, it's too bad. I would love to make an amusement park ride where you could actually feel this pressure, where you would be like, "Whoa, I took a step back because I was traveling in a circular environment going up something." You know what I mean? But even the fastest elevator isn't enough to, like, you know, feel like an eyelash. I think it's a tenth. I think it's like a tenth of an ounce. That's the pressure you would feel. Maybe it is like 1 ounce, but that's the entire pressure you'd feel on your entire body if you put your back up against the elevator. Not much. Okay, so whoa! I think just naming that Coriolis acceleration is the dumbest, but I guess it's a guy. You know, again, everything that's named after somebody, I don't know, man. I think there should be, you know, get over it. Now, alright, my camera cut out, but we're basically done. And no, it's just kind of fascinating. I always thought Coriolis was like some sort of Latin for like moving, swirling current. Like, that's so fast. I've never even heard of the dude Coriolis. I don't even know his last name. But this book says that the Coriolis effect was G.G. Coriolis. We don't even know his first name. Greg. Anyway, sweet. So, Greg Coriolis. No, I'm just kidding. But Coriolis. Yeah, it's so fascinating. But anyway, I think, yeah, it is it's what causes, you know, like if you have two different air layers and they're moving with the Earth, like one is definitely, I don't know, moving faster. But yeah, if you have oh, this is what happened. Yeah, no doubt, Coriolis effect, especially when you have like warm air rising, then it's hitting like faster moving molecules, you know what I mean? If you have a column of air that's moving, something has to actually push it. To just move straight up in the atmosphere, you have to have a force, the Coriolis force, to keep it on that trajectory. Else, it's not. That's where you're going to get this. Like, if the Earth is rotating this way and you do have a thing that moves up, it would just make sense to curve this way. That's no Coriolis acceleration. That's what it wants to do. It doesn't want to go up the elevator. It actually requires a force to push you in line. So that's kind of fascinating. It's the equal and opposite of a circle. Like if you're on a circle, you want to go tangentially, but you had to go towards the center. Where this is, you actually what is that right? This is a relative picture, and we're done. So anyway, but yeah, I'll try to do more videos. Oh man, I guess I learned a lot. I really didn't learn anything. That's the tricky thing, is I'm just going over the stuff that I know. But I think that's a good aspect. And what I don't want to do is just use these dumb equations without understanding them. And without even a teacher, they're not going to tell you, they're not going to do what I can do later on. But I can't do this stuff until I have like kind of a general understanding. Who knew? I didn't even know it was even called Coriolis acceleration. Like, I've always known that, hell yeah, if you're rotating and you're moving in this direction, you're going to have an acceleration in the tangential direction due to, I guess, the Coriolis effect. And hopefully I'm saying that right, but I just know it as like the elevator effect. Alright, hell yeah. So thanks for joining me on this one, and guess what? That's a video.